What is A? So, welcome to today's episode of Chemistry with Elite. So, let's assume you have a question of benzene attaching to amino group, that's amine. This is aniline. Aniline with NO2 plus. What is the product we are going to get? Now, let's take note that this is a very good example of the electrophilic aromatic substitution of benzene. But now, it's actually going to be disubstituted. Why is it disubstituted? Because we already have an electrophile on the benzene ring already. Now, want to attach another electrophile to it. So it is actually two. That's why we call it a disubstituted benzene ring. Now, if we want to disubstitute benzene, we actually have three positions that the incoming new electrophile can occupy. Electrophile is a group that is positively charged or a group that is electron deficient, does not have enough electron. So that's why it is positively charged. Now, this can actually attach itself to 1,2 disubstituted. The 1,2 disubstituted is what we know as the ortho position, or the 1,3 disubstituted. The 1,3 disubstituted is what we know as the metal position, and it can actually be 1,4. The 1,4 is the what? Is the para position. So these are the positions that this NO2 plus can occupy, either ortho, metal, or para. And take note, all these two, this is a cyclic compound. I can either count this way or count the other way. So that means this is also ortho, and this is also metal, and this remains para. Do you understand? So this is over. Now, the NO2 group, where is it going to occupy? Is it the ortho, the metal, or the para? Now take note, what determines the position of the new incoming electrophile is the group that is already attached to the benzene ring. If the group is actually an electron withdrawing or electron donating, if it's actually an activator or a deactivator. Now, NH2, which is an amino group, is it an activator or a deactivator? An activator is still electron donating, and a deactivator is electron withdrawing. Now, NH2 is a very good example of electron donating group. It's an activator. So this NH2 has the ability to give the ring more electrons, and once the group that is already existing on the metal group is an activator, the position of the incoming group can either be ortho or para. If it's an activator, it's actually going to be ortho or para. If it's a deactivator, it will only be what? Metal. You might be thinking, how? Why? Let's look at it together. Let's look at the mechanism. So, activator, like I said, is any group that can give out electron. Now, let's assume that this NH2, since it has lone pair of electron, it gives this group or this cyclic compound the electron. Now, if it gives it the electron, let's look at what we are going to have. Then we are going to have something like this. Good. Now, this will not be double bonded to NH and 2. Since this gives out a new electron, good. Since this is giving out a new electron, it's going to be positively charged. Now, we are giving this is giving this group an electron. Automatically, this one will actually move because that's resonance. So this will move to this carbon. Once it moves to this carbon, then what are we going to have? If this moves to this carbon automatically becomes negatively charged. Now, if it becomes negatively charged, we have this, we have this. Now, don't forget it's plus NO2 plus. Whenever we see positive and negative, what will happen? They will attract, which means that this man can actually take the ortho position. Are we good? But this does not actually stand like that. We can still move the electron. Now let's imagine that we move this electron again, we move it down. Now if this electron moves down here, if this negatively charged moves down here, this becomes double bond, but this will not stay like that, so it will also move. So it will move on this particular carbon. Now if it moves on this particular carbon, let's look at what we are going to have at the end of the day. We are going to have the benzene ring normally, our normal benzene ring attached to the NH2 that is positively charged, double bonded. Now this is coming here, so we have a double bond here. Now this is coming on this particular carbon. This particular carbon becomes negative, and then we have our what? Our double bond, and it is still plus what? NO2 plus. Now this positive can also be attracted to what? Negatively charged. So because of this, you can see no matter how we continue moving it, the negatively charged will always always fall on the auto and the what and the para. Since the group that we have here is an activator. An activator is that group that can give the compound and that can give the cyclic compound the electrons that it has. So once if I continue moving this, you realize that where to always fall will always be on the metal and on the auto and on the what on the para, since it's an electron donating group. But if it's an electron withdrawing, what are we going to have left? Now let's look at what we are going to have left. Now for electron withdrawing group, a very good example of an electron withdrawing group, we have Na2, we have RCO, that means the carbonyl group, we have SO3. Those are electron withdrawing group. But let me use RCO, that's the carbonyl group, as a very good example of a deactivator here, or electron withdrawing group. Now what are we going to have? Let's see. We have something here. Good, let me use this. So let's say we have this, the benzene ring, the 1, 2, and 3, the benzene ring attached to RCO. Good. Now this is what we have. So let's say we have this plus an incoming group. Let's say it's still our NO2 positive. What position will this occupy? Is it the auto, metal, or the para? Now, since this is a deactivator, electron withdrawing, not electron donating group, we know that the position we should take is what? Is metal. Because I already mentioned it now that if it's electron donating, for electron donating group, it will be auto and para. But electron withdrawing is going to be metal. But why is it metal? Let's see why it is. The position is going to be metal this way. Good. Now, electron withdrawing, like I said, is taking electrons from the group. Now, if this thing is taking electrons from here, that means instead of the electrons to come down, it will be moving up. We are taking it away. Look at this. We are giving it. But here, we are taking. So if we take it away from here, then we are going to have something like this. Now, this is moving. This is moving there. So if this is moving, let's see what we are going to have. So this is going to be something like this. We have the benzene ring. Good. The benzene ring. Now this is now going to be double bonded to C. Then we have arrow. Since this is moving now, we have a double bond there. The double bond here will move to this particular oxygen. So if it moves to that oxygen here, then we are going to have O negative. Now what are we going to have left in the group? We have a normal double bond. Nothing's happening to this. We have this. This one that moves. This, since it's moving away from this carbon. If you are taking electrons away from a particular element, it becomes what? Positively charged. So here becomes positively charged. Why is it positive? Because we are taking the electron away from it. So here becomes positive, and this is what? NO2 positive. Now, according to law of electrostatic that we still use here, like charges repel and like charges attract. So since this is positive and this is positive, this cannot occupy the auto position. Why? Because they are positive. Rather, it will look for a place that is not positive to attach itself to. Are we good? Now this is what we have. This can be one. Another one that we can have is that, okay, this electron here, this one too can also move here. If this moves here, let's look at what we are going to have. Good. We have this. We have O negative connected to R. Now this is our double bond. Nothing happening to this one. Now if this thing moves to this side, don't forget that we are moving the electron away from this particular carbon that is here. So since we are moving the electron away from this particular carbon, that means the last carbon that we have down here becomes positively charged. So here becomes positive, and then we have our double bond. We have our double bond here. So our double bond is going to be here. So here becomes what? Positively charged. Now plus our NO2 positive. Since this is also positively charged, that means this cannot occupy the para position because they are the same charge. So the only side that NO2 will prefer to attach itself is where it's not positively charged. And out of where it's not positively charged that it can attach itself to is actually on the what? On the metal. So whenever we have a deactivator or electron withdrawing group attached to a benzene ring, the disubstituted that is going to attach itself to the benzene ring will actually attach itself to the what? To the metal position. Shall we get? So let's take note of that. So when we are having an electron donating, this electron donating is actually going to be auto or para. We call it auto para position. But if it's actually an electron withdrawing, for electron withdrawing, where we are going to attach it to is at the metal position. So let's take note of that. Very, very important. So the product A that we are going to have here is going to be something like this. Good. This here, and this here. And then we don't forget we have our NH3. Then it can actually attach itself to this. We have our NO2. Or we can also attach it here. So that is what we have for this. And for this we are going to have something like this. Good. We have C double bond O. We have our R. We have double bond here, double bond here, double bond here. Since this is actually electron withdrawing, we know it should actually take the what? The metal position, which is NO2. And please take note that this is NH2. Good. So this is what we are going to have as our final product. Now, out of all these steps, where we attach the NO2, where we break the bond between C and H group, where is the rate determining step? How can we get rate determining step of all this kind of reaction, either the monosubstituted or the disubstituted benzene? What is the rate determining step? I'll be making another video explaining how we can get rate determining step for electrophilic substitution reaction of benzene. And watch out for one of our videos coming on soon. Does benzene undergo nucleophilic substitution reaction? Because this is an electrophilic substitution reaction. Does it undergo nucleophilic too? One of our videos will be explaining that. Take note. Remember to like, share, and comment on this video. Thank you so much.